Welcome back, everyone. So, have you ever thought that what are column spaces? If not, then this video is for you. So, the visualization you are seeing right now in front of your screen, here, this gray YZ plane is nothing but a column space. This is a column space of a matrix, and the vectors lying in this column space, that is a green vector, the blue vector, and the purple vector, is nothing but the column vector of the matrix corresponding to this column space. So in today's video we will see what are column vectors and what are column spaces. So let's begin. Okay, so this is a matrix A 3 by 4 matrix, 3 rows and 4 columns. This is a difference matrix, by the way, so we will see what is a difference matrix. But yeah, so okay, so you can these columns of the matrix are nothing but vectors, right? So this happening, just give me yeah. So this can also be written as A1, A2, A3, A4, right? Where A1, A2 are column vectors. All right, A1, A2, A3, A4 are column vectors. That is the column of the matrices. Okay. Now, if you take this matrix vector product, that is, you take the uh, matrix A and you multiply it with a vector X. So, what does this mean? So, there are two interpretation to this. There are two interpretation to this matrix vector product. Is one is the row interpretation, and one is column interpretation. All right. So what is row interpretation or row picture? So in the row interpretation, AX will come from dot products of X with the rows of A. So we have this matrix, right? And then we are multiplying it with the vector X, X1, X2, X3, X4. So the row interpretation is nothing but it says that each rows of A, these rows of matrix A multiply with the column vector X. Okay, so these multiplications are nothing but row times the column. I mean, these are the dot products. So it will something look like it will look like this. So it is nothing but row 1 dot product X, row 2 dot product X, row 3 dot product X. Okay. So what is I will simply write what is row 1 dot product X. So what is row 1? Row 1 is nothing but minus 1 1 0 0, right? And you take the dot product with vector X, which is x1, x2, x3 and x4, right? So this will simply become x2 minus x1, right? So this row interpretation is nothing but you're simply taking the dot product of every row of the matrix with that vector. Okay, so this will this matrix vector product will become x2 minus x1, x3 minus x2 and x4 minus x3. Okay, and this is why this is a difference matrix, because you can see that it is nothing but we are taking the difference of the components of vector x, x2 minus x1, x3 minus x2. All right. So this is one interpretation of the matrix vector product AX. Okay. Usually we solve whenever we solve questions, we multiply a matrix with a vector. We follow this approach only. while doing that matrix vector multiplication. But there is one more interesting interpretation or interesting picture, the column picture or the column interpretation of it. So the column interpretation is more important and beautiful because it is related with the to the column space. So the column picture of AX is the matrix A times the vector X is nothing but the combination of the columns of A. Okay, so it says that AX is a combination of the columns of matrix A. This is the column interpretation. All right, this is the column picture. All right, and this is the row picture or row interpretation. So AX is nothing but x1 times uh, column A1 plus x2 times column A2 plus x3 times column A3 plus x4 times column A4. Now here x1, x2, x3, x4 are component of vector x. So these are nothing but scalars. But column A1, column A2, column A3, these are these columns. So these are column vectors. So these are not normal scalars. These are vectors. So this is nothing but scalar vector product, right? X1 is the scalar. Then you have this A1 vector, column vector. X2 is the scalar. Then you have A2 column vector. X3 is the scalar. Then you have A3 column vector. And X4 is the scalar. Then you have A4 column vector. All right. So if you expand this is nothing but x1. What is the first column vector? It is -1, 0, 0. Then x2, the second column vector, 1, -1, 0. Then x3, the third column vector, 0, 1, -1, and then x4, the fourth column vector, 0, 0, 1. And when you expand it, you will get the same result: x2 minus x1, x3 minus x2, and x4 minus x3. So see, both the row interpretation, the row picture and column picture give you the same result. All right. It's just that they have different meaning. The row interpretation is taking the dot product of each row of matrix A with the vector X. Whereas the column interpretation is something interesting. It has some visual interpretation as well. It says that this matrix vector product is nothing but taking a linear combination of columns of A. This is the column interpretation. So we are taking a linear combination of column of A. So what is this? This is linear combination, right? We have studied this. This is nothing but linear combinations. Linear combination of columns of A, right? This is linear combination of columns of A. All right. Now we will see, we will try to visualize this. Okay. We will try to visualize this. So let us suppose this is the first column vector of matrix A, that is A1. This is the first column, the A1, which is a column vector. And let us suppose uh, this is basically this is the second column of matrix A, the second column vector A2. Now let us suppose we combine these two columns. We combine these two columns, column vector A and column vector 2 of matrix A. So let us suppose we combine such that 2A1 plus A2. Okay, we take the linear combination of the columns, the first two columns of matrix A. So basically this will look something like this. 2 times A1, basically you just stretch it twice, right? So somewhere here. So this is 2 times A1, right? Now if you want to add A2 to it, you just take this vector and place it here, right? Place it here. The tail of it goes to the tip of 2A1. So this becomes A2. and this is your addition of those two vectors. All right, so this is nothing but 2 times a1 plus a2. All right, so this is the linear combination. Now, this is one of such linear combination of a1 and a2, right? But if you need to generalize it, if we take all the linear combination of the first two column vectors of matrix A, that is alpha times a1 plus beta times a2, then how it will look like? Let's see. So it will look like something like this. So first of all, we will see what is alpha times a1. I said that this is nothing but span of vector a1. What is a span of vector a1? Basically, all the linear combinations of the vector a1. So because it's the vector alone, so you just need to scale it. So alpha times a1 is just nothing but the line passing through the vector a1. This is alpha times a1, right? This line is nothing but alpha times a1. You just take all the possible scaled version of a1. The same thing goes for this beta times a2, right? This beta times a2. You just scale a2. You take all the scaled versions of a2, or you can say this is nothing but the span of vector a2. All right. So this is beta times a2. Now 2a1 plus a2 is one such a special case where alpha is 2 and beta is 1. And this is the case where alpha is 2, this becomes 2a1 and the beta remains 1. So this remains a2 and you get this this vector 2a1 plus 2a2. Basically this vector, right? Now when you take all such linear combination, you will get a plane. You will get an entire plane passing through vector a1 and a2. Okay. So all such combination is nothing but the linear combination of two vectors a1 and a2, because these are not linearly dependent. So the linear combination of this vector a1 and a2 is nothing but this entire plane. This entire plane. This is the first axis. This is the second axis, and this entire plane is nothing but all the linear combination of the first two columns of matrix A. Because see, the columns of matrix is nothing but vectors. These are column vectors, and the entire theory goes as it is, right? We have seen the span of two linearly independent vectors is nothing but a plane, right? So columns of A are also vectors. So the span of two columns of A, which are linearly independent, is going to be a plane only, right? So similarly, if you take the span of three columns, because these are linearly independent, then the span of three columns will be R cube, that is the R3 space, and the span of four columns will be, if all the four columns are linearly independent, it will be the R4 space. Okay, so this is the row picture and this is the column picture. So you see the row picture is simple, that we are the row picture is more about dot products, that is taking the dot product of the rows of matrix with the vector. But the column picture, the column interpretation is something beautiful, because it is saying that the matrix vector product is nothing but a linear combination of columns of matrix A. So we are taking the linear combination of columns of matrix A, or linear combination of column vectors. All right. So this is connected to column space. Okay. So we will also see this independent and dependent column. Okay. Because I already told you that uh, just give me a minute. Independent and dependent columns. Okay. So because I told you that columns of matrix A are column vectors, right? These are just vectors, and I already explained you independence and dependence of vectors, right? in this lecture I already explained you everything, linear dependence and independence of vectors. So the same things goes for columns. The same thing will go for column of A also, because column of A are nothing but vectors, right? So for example, let us suppose we take this matrix, all right, this matrix 1 2 3 0 4 5 0 0 6. All right. So these three columns are linearly independent. Okay, I will show the visualization. These three columns are linearly independent. So if these three columns are linearly independent, then their combination, their linear combination will fill the entire 3D space. Okay, so the linear combination of columns of A1 will fill entire 3D space, that is R cube. All right, so let's see this the columns, how it looks like. So this is Desmos, all right. So this is the first column, 1, 2, 3. All right, this is the first column, 1, comma 2, comma 3. Okay, you can see it is lying in the 3D space, right? Now this is the second column, that is 0, 4, 5, 0, 4, 5, right? So this is the 0, 4, 5. It lies in the YZ plane, right? Because the X component is 0, so it lies in the YZ plane. And this is the third vector, that is 0, 0, 6. It lies in the z-axis because the first two component 0, 0, x and y component are 0, so it lies in the z-axis. Okay, now let us suppose we first start with the third one, that is this vector, right? The span of this vector is the entire z-axis, because you scale this vector, you will remain in the z-axis only, right? Now you take the second column vector, that is 0, 4, 5. Now tell me one thing. There is We cannot get this green vector from this blue vector. That is the third column vector. We cannot get the third column vector from the second column vector. Why? Because see, uh, to get this vector from the green vector from blue vector, you need to take some linear combination, right? But this blue vector, this blue vector, you can only scale it, right? Any linear combination of this blue vector will remain in this line, which is passing from the blue vector, right? So you cannot get this green vector at all. So that's why these two vectors are linearly independent. Okay, and what is the span of these two vectors? The span of these two vectors is the YZ plane. All right, the span of these two vector is the YZ plane. Okay, so the span of these two vectors is this YZ plane. You can see that both these vectors are lying in this plane, right? Now we take the third column, the first column vector, that is 1, 2, 3. We have taken the second and the third and second column vector. Now we will take the first column vector, 1, 2, 3. Now we will see this 1, 2, 3. See, this 1, 2, 3 is lying outside this plane, right? So is it possible to get this first column vector 1, 2, 3 from any linear combination of the remaining two column vector? No, not possible. We have seen in the previous lecture, sorry, we have seen in the previous lecture that uh, the linear combination of these two vectors, because these two vectors are lying in this plane, this YZ plane, right? So the linear combination of these two vectors always remain in this plane, this YZ plane. But the first column vector 1, 2, 3 is outside this plane. So it is impossible. There is no way you can combine these two column vectors, the column vector 2 and column vector 3, the second column vector and the third column vector. You cannot combine them in any way to get the first column vector, because the first column vector is lying outside the plane containing these two column vectors. All right. So that's why you take the span, you take the linear combination of the second and third column vector, you get some vector, and then if you take the linear combination of that resultant vector with the first column vector, you will get outside this plane, and that's how these three vectors combined are filling this entire 3D space RQ, right? But let us suppose instead of this we have this one. Uh, 0 4 5 0 0 6, but the first column vector is not 1 2 3, but it's the addition of column 2 and column 3, so 0 4 and 11. Let us suppose this is the case, right? So if we see this, this is 1 1 6. So let us suppose this is 0 4 and 11. All right, let us suppose this is the case. Now if you see the third, if you see this third one, right, these two remain the same, okay, but this one has changed to 4 0 4 11. So now if you see this third bigger vector, the purple vector, it still remains in the same plane, right? It still remains in the same plane. So this purple vector can, we can get the purple vector from a linear combination of these two vectors, green and blue, right? Right? So that's why we can say that these three column vectors are linearly dependent, because the first column vector is nothing but a linear combination of the second, the remaining two columns. So basically, uh, column A1 is nothing but column A2 plus column A3. Okay, so we can simply say that their combination don't fill the 3D space. So the linear combination of columns of A2 columns of A2 doesn't fill the 3D space. It just remain in the plane, because the first vector is nothing but a linear combination of the second and the remaining two vectors. So it remains in the same plane. All right. And that plane, okay, this plane, this plane, that is all combination of the columns. This plane is the column space of this matrix. Okay, this plane is the column space of this matrix. So in A1, the column space is nothing but the entire 3D space. All right, so that's all for this lecture. In the next part of column space, that is column space part 2, we will deep dive into column space further. We will see the formal definition of column space and what they are in detail. And we will also see all the possible column spaces of the R cube vector space, that is the entire XYZ volume. All right. So if you found this video helpful, then please like it and subscribe my channel. And also please share my channel and videos with other GATE aspirant and machine learning engineer and researchers. So thank you for watching this video. See you next time. Bye.